Hi everyone, I'm Nate and welcome to Elevate with Nate, a place for learning, growth and self-improvement. Join me as we explore a wide range of topics, sharing insights and new knowledge from my personal learning journey. Today we're tackling a fascinating question, which is, why is it often faster when travelling by plane to take a route which on a 2D map appears longer than going direct? So for example, when travelling from London to LA, or let's say the west coast of Canada, such as Vancouver or Calgary, the plane will often go kind of north over Greenland and come back down. So why is it faster doing this route? So let's dive into the geography and the maths behind this. When we look at a 2D flat map, which are called Mercator maps, it's very easy to think that you can just draw a straight line, let's say LA to London. But that's not quite the case for the fastest or shortest distance, because the Earth is a sphere. Think about this. If you took that 2D map and try and wrap it around a sphere, you'll find that it won't perfectly fit, okay? So instead, looking at it the other way around, if you took a globe and let's say you tried to kind of like make an insertion and kind of cut it out and lay it flat, what you'll find is it won't create a rectangle, it will create a different shape, which can be shown using something called a azimuthal map, shown here. And on that new map, we can see is quite clearly the shortest distances. And it looks very different to what you're used to looking at in a usual 2D map. And on here, if let's say we take the same example with LA to London and vice versa, you can see that if you draw a straight line, you'll be going over, say, Greenland. And what that means for the usual flat 2D Mercator maps is, if you actually right now look at the map, you've of course got your longitude lines and latitude lines. As you kind of venture further away from the equator, kind of go either north or south, the linear, say, scale factor actually increases as you get further away from the equator. So that means is the country further north on a usual flat 2D map will look larger than they actually are in real life. So for example, if you compare, let's say, Iceland and Spain on a flat 2D Mercator map and then the azimuthal map, you will see that as a bigger difference. Let's say Iceland will appear bigger compared to Spain on the 2D map as opposed to the azimuthal map because it's further north. Right, so the next obvious question to ask would be, well, how do you find the shortest distance between 2 points on a sphere, not a 2D map? And this is calculated by looking at something called a great circle. So a great circle is any circle which divides a sphere directly in half, okay, into two equally sized hemispheres. So hopefully, if you kind of think about this, you can take any 2 points. With any 2 points on the Earth, you can kind of make a section through it, which will also go to the centre of the Earth to make a perfect hemisphere. And now, kind of looking at it sideways on, the arc on that, let's say the circumference of that circular face, the arc between the 2 points will be the shortest distance. Right, so hopefully now you understand exactly why the flights you take aren't always direct when looking at a 2D flat map, okay? And you know that you must do the cross sections to find the great circle, to find the arc, which gives you the shortest distance. I'm going to right now go into briefly the maths behind how to find the actual distance of that arc. But just bear in mind, it is some pretty complex maths here, so feel free to skip ahead if maths isn't your thing. If it is your thing, then listen in. Let's break down the maths then. So we're trying to find the shortest distance between 2 points on a sphere. And this distance we call the geodesic distance. And actually we can work this out using something called the Haversine Formula. Now it turns out that Haversine is actually a trigonometric function. Now hopefully most of you will have heard of sine, cosine and tangent, tan. But back in the day there were actually many, many more, including, read the list here, Haversine, versine, covasine, haversine, exsecant and excosecant. Hopefully I didn't butcher too much the pronunciation, apologies if I did. But these are now obsolete, as all of those trig functions can be expressed as a combination of the three main ones, sine, cosine and tan. So let me speak a bit more about what Haversine actually is. So looking here at my screen, you can see that, well, firstly, you've got here the unit circle. Okay, that means that has a radius of 1. And what hopefully you might recognize is, of course, if you have 1 cos theta, okay, that gives that distance there, the bottom of that little triangle, and sine is the opposite side of that triangle. But we now have something called versine, okay, and that is the distance, the remaining distance on the x-axis between the cos and the length of 1, the radius. That's versine. And what we call haversine, it's the half versine. It's essentially half of versine. So here it is. It is haversine theta is versine theta divided by 2. So that's what haversine is. And from here, you can also see other of the distances or the functions I mentioned previously, such as x second, etc. And if you look below here, you can see that we express haversine also as sine squared theta divided by 2. So let's now look at this page, which will show you what the actual Haversine formula is. So just before we start that, you can see at the top here, theta equals d over r, where d will be the distance we're looking for, that arc length on the sphere. And you can see on the diagram here, it is the red line. And this simply comes through if you think about taking the center of the circle and connect it to Q and P with a radius. That note is simply a sector of a circle, and that will be our the arc length is our theta in radians. So that is a simple rearrangement to give you theta equals d over r. And below that now, here we have the Haversine formula, which is Haversine theta is Haversine delta phi, the change in phi, plus cos phi 1, cos times cos phi 2 times Haversine the delta change in lambda, where here the phis represent the latitude of your points, and the lambda is going to be the longitude of your 2 points. So hopefully that makes sense. And just a quick one here too, you can see that sine squared theta over 2 equals 1 minus cos theta over 2. And that comes from, if you know, that cos 2 theta equals 1 minus 2 sine squared theta. Half the angle, rearrange, give you that. So before we now break down exactly how to therefore work out an explicit expression for d, let's just go to the actual the proof to work out actually the Haversine function. And I'll go through it quite quickly. But just here we have, of course, the 2 points, P1 and P2. That's our 2 points on our sphere. And we are going to express it in terms of the longitude and the latitude. And here we also have it now, of course, it's a 3D shape, so it's got its 3D coordinates, which are expressed right here as P2 and P1. Here's a nice bit though. We're going to, in a bit, use the dot product to find an expression for the angle. But if you think about this, right, if you rotate the sphere along its z-axis, into the page, okay, what will happen there is, even though your longitude will change for your 2 points, the latitude won't. And on top of that, there'll be a constant, say, factor of change as you rotate this. So if one goes, say, 2 to the right, so will the other one. And they're quite sneaky here. What they do is they go, right, let's say, instead, let us, say, shift this and rotate this by a factor of, say, minus lambda 1, the first longitude of one of the points. And what will happen here is the P2 will now be cos lambda 2 minus lambda 1, but they just call lambda dash this expression, because delta lambda, which you have here, is just lambda 2 minus lambda 1. So now you've got the same expression for P2 is now with lambda dashes on it. However, for P1, cos lambda 1 minus lambda 1 is just cos of 0, which becomes 1. So 1 times cos phi 1 is just phi 1. So it becomes a bit more, it's a bit neater. It's a nice little trick here to get nicer expressions, and it won't affect the actual maths behind this. Now at this point, if you do a bit of dot product, just work through it first if you know how dot product works, and eventually going to get to this line here involving some causes. And the only kind of slightly tricky bit here is, well, how are you going to go from this expression with causes to now having some haversines too? And if I just show you this little screenshot, say the next one, sorry, where is it? here we go. This will show you a bit neater how it's done. Because from before, as we explained with the causes and the haversines, remember that expression, 1 minus cos over 2, you can rearrange this that cos delta phi is 1 minus 2 haversine delta phi. And all we do here is we sub into the top line, which we had beforehand, 1 minus 2 half, and the same for the right. A bit of kind of tidying up here because minus 1 plus 1 goes to 0, goes away, and there's nothing too much tricky going on here. You just keep subbing into cos thetas for 1 minus 2 half thetas and solve for half theta. And that gives you, at the very bottom, the equation which we want. The half theta is half delta phi plus cos phi 2, cos phi 1 half, basically delta lambda. So there is the proof for the Haversine function. So very quickly now, let's see if we can now make some headway into how to actually now find d explicitly. So here we have the expression, and where this comes from is, if you rearrange that top one, the easy one, you have that d is r theta, as we should know. But now let's express theta in terms of the Haversine's function, okay, it becomes a formula. And we have here either you're doing simply arc, so inverse Haversine, or rearrange for inverse sine from the obviously the equation above here. Okay, you're gonna have to do square roots and rearrange and arc sine, giving you d equals 2r arc sine root half theta. So at this point here, just going below, I'll explain the first 3 lines. I think that's pretty good enough for you to kind of input values and use it yourself. But you simply plug it in. So half theta we have from before in the big equation, you plug it in, and now you simply rewrite half delta phi as what we had before, sine squared delta phi over 2. And here is simply, I think, the last kind of harder bit. It's how does it go from having this bracket, 1 minus sine squared, etc. minus sine squared, to being cos phi 1 times cos phi 2. And if I share this screen with you now, you'll be able to see exactly where this comes from. So this expression up here we had from before, no change here. And what it's saying is that because we know this, we can sub that back into that equation before. So if I go back here, we can exchange, where is it? Did this one here for the new expression. But also therefore the same thing for 5m, which by the way, 5m was simply name given for phi 1 plus phi 2 over 2. So plugging this into the same expression, of course we know that this angle here is always double. If you double phi 1 plus phi 2 over 2, you get just phi 1 plus phi 2. And if you scroll down a bit here, finally, we now just sub that back in to get this expression on the right. And so I'm mopping up here, you go times by 2, common denominator, and what will happen here is all the numbers will go, leaving you just with plus cos delta phi plus cos phi 1 plus phi 2. But remember, delta phi is going to be phi 2 minus phi 1. And this is essentially just the sum to product identity. So phi, cos of phi 2 minus phi 1 plus cos of phi 2 plus phi 1 equals cos phi 1 times cos phi 2, which leads you to back to here, while we go from this bracket down to this expression here. Okay. Now to go from the third line to the fourth and fifth line, it's some even more complicated stuff. So I'm gonna leave it right there because hopefully you yourself can have a calculator right there and can use your cos and sines. At that stage, you're good to go. Also, you're good to go also on the second line, but it's a bit neater, that third line than the second line. So hopefully you enjoyed that. It makes a bit more sense on the maths behind the Haversine function, and how to work out the shortest distance around a sphere. Thanks for watching. If you enjoyed this video, please give it a thumbs up and hit that subscribe button and bell notification. Feel free to leave any comments and any suggestions for future content. And as ever, onwards and upwards.